Let us now start the discussion on module 4 of chapter 9. In the last module, we have formally defined the notion of abstract measure mu on a ring R and the notion of an outer measure mu star on a hereditary sigma ring. We have seen that from a given measure mu on a ring R, we can extend it to an outer measure mu star on the generated hereditary sigma ring HR. And subsequently, we had defined the notion of mu star measurable sets as some special subsets of HR. We have shown that the members of this special collection, which we denoted by S bar, it forms a sigma ring and it contains the class of sets from the ring R. Now, in this module, we are going to show that in this process, we can actually extend the given measure mu from the ring to a sigma ring, and we will also examine its unicity and some other results. We start with this theorem. Let mu be a measure on a ring R and let mu star be the extension of mu to an outer measure on HR. Let S bar be the collection of all mu star measurable sets, and let us write the restriction of mu star on S bar by mu bar. Then mu bar is an extension of mu to a measure on S bar. For the proof, observe that obviously mu bar is non-negative with mu bar phi equal to 0, and mu bar is an extension of mu because mu star is already an extension of mu and mu bar is the restriction of mu star, which contains the ring R. We know that if we take a member A from HR and n belonging to capital N is a sequence of pairwise disjoint measurable sets, then mu star of A intersection union I equal to 1 to infinity E I is equal to sigma I equal to 1 to infinity mu star of A intersection E I. Now, in the above equality, let us put A equal to union I equal to 1 to infinity E I, because since S bar is a sigma ring, the set A belongs to S bar, and consequently, we have mu star of union I equal to 1 to infinity E I is equal to sigma I equal to 1 to infinity mu star of E I. Now, see that since all the sets E I and union E I are measurable, we can write mu bar in place of mu star, and this shows that mu bar is countably additive, and so mu bar is a measure. Now, the question is that from a given measure mu on a ring R, we have extended it to a measure mu bar on a sigma ring S bar containing R. We already have observed that from a given measure on a ring R, we can extend it to an outer measure mu star. So, the natural question is that if we start with the measure mu bar instead of mu, then what will be the resulting outer measure? Will it be different from mu star? This theorem gives us the answer that the answer is no. Even if we start from the extended measure mu bar, we will still get the same outer measure mu star. So, see the statement of the theorem. Let mu be a measure on a ring R and let mu star be the extension of mu to an outer measure on H R. Let S bar be the collection of mu star measurable sets and mu bar be the extension of mu to S bar. Then mu star E have two equivalent criterias. The first is we can write it as infimum of mu bar f, where E subset of f and f is a member of S R, the sigma ring generated by R. At the same time, it can be written as infimum mu bar f, where E subset of f and f comes from S bar. First thing you should note that since R is subset of S bar, so H R is subset of H S bar. But on the other hand, since S bar is subset of H R and H R is a hereditary sigma ring containing S bar, H S bar is the smallest hereditary sigma ring containing S bar. So, H S bar is again subset of H R. So, we have H R equal to H S bar. In other words, instead of starting from the original ring R, if we start from S bar, a larger class, we still get the same hereditary sigma ring. Now, let us take an arbitrary member E from H R. By the definition of mu star E is equal to infimum sigma n equal to 1 to infinity mu of E n, where E is subset of union n equal to 1 to infinity E n, where the sets E n come from the ring R. This is obviously greater or equal to infimum sigma n equal to 1 to infinity mu bar E n, where E is subset of union n equal to 1 to infinity E n and E n comes from S R. Since S R is a larger class, so we have more covers and correspondingly we have more numbers, so the infimum becomes less. Now, since S R is a sigma ring, So, union n equal to 1 to infinity E n, if we write this set as F, then the set F belongs to SR. Also, from the countable sub-additivity of the measure mu bar, we already have mu bar f less or equal to sigma n equal to 1 to infinity mu bar E n. So, we have mu star E greater or equal to infimum mu bar f, where E is subset of f and f comes from SR. So, we are replacing the summation sigma n equal to 1 to infinity mu bar E n by a smaller number mu bar f. So, the infimum becomes less, and this is again greater or equal to infimum mu bar f, where E is subset of f and f comes from S bar. Here again observe that as SR is subset of S bar, so we have more options of f, hence the infimum decreases more, but still this is always greater or equal to mu star E by the monotonicity of mu star, because in any case the set E is subset of all these f, and consequently mu star E is less or equal to mu star f, which is equal to mu bar f. So, combining we have this particular inequality like A greater or equal to B greater or equal to C greater or equal to A, but this implies that all the three numbers A, B, C should be equal, and this proves the result. From the construction of mu star, it follows that if the original measure mu is sigma finite on the given ring R, then the resulting outer measure mu star defined on H R is also sigma finite, and consequently the measure mu bar on S bar is also sigma finite. But in general, this extension of measure from a ring to a sigma ring is not unique. So, in the next theorem, we are going to see when this extension is unique. Let mu be a sigma finite measure defined on a ring R, then mu has an unique extension to a sigma finite measure mu bar on S R. We start the proof. We already know that if mu is sigma finite, then the extending measure mu bar is also sigma finite. To prove its unicity, we have to show that if we take another sigma finite measure mu 1 on S R with the property that mu 1 equal to mu bar on R, we have to show that mu 1 coincides with mu bar on the whole of S R. So, let us start with the assumption that at least one of the two measures is finite. Let M bar be the collection of all those members for which mu 1 is equal to mu bar. Now, clearly see that since both mu bar and mu 1 are extensions of mu from R. So, on R they are both equal. So, R is subset of m bar. If we take a monotonic sequence E n from m bar, then we have mu 1 of limit n E n is equal to limit n mu 1 of E n, but this is equal to limit n mu bar E n. This is equal to mu bar of limit n E n. So, this shows that for a monotonic sequence E n coming from m bar, limit n E n again belongs to m bar, and so m bar is a monotone class. But we already know that R is subset of m bar and SR is a sigma ring, and so is the smallest sigma ring containing R. So, SR should be subset of m bar, and this shows that mu 1 should be equal to mu bar on the class SR. Now, consider the general case. Let A be any fixed set in R of finite measure with respect to one of the two measures mu 1 and mu bar. First, observe that since both mu 1 and mu bar are sigma finite, so such a set A always exists. Now, R intersection E is again a ring, and we have already proved in the first module of this chapter that S of R intersection A is equal to SR intersection A. So, we have mu 1 E is equal to mu bar E for all E belonging to SR intersection A. Since every E belonging to SR can be covered by a countable union of sets of finite measure taken from R with respect to either of the measures mu 1 or mu bar. So, it now follows that mu 1 should be equal to mu bar on the whole set S R, and this proves our assertion that if the original measure mu is sigma finite on the ring R, then the extension mu bar on SR is an unique extension of the measure mu. Next, we are going to present an interesting definition. Let mu be a measure on a ring R, and let mu star be the extension of mu to an outer measure on HR, and as always let S bar be the collection of mu star measurable sets. Let mu bar be the extension of mu to S bar. A mu star measurable set F is said to be a measurable cover of E coming from HR if E subset of F and for any mu star measurable set G contained in the difference F minus E, we have mu bar G equal to 0. The notion of this measurable cover comes from the theory of Lebesgue measure. Recall that we have seen in the chapter on Lebesgue measure that for any set of real numbers A with finite outer measure, we can find a G delta set G which is obviously measurable such that mu star A is equal to mu of G. So, there that G delta set is a measurable cover of the set A. Now, the question is, for an abstract measure defined on a ring R, which sets will have a measurable cover? So, we answer this question with this theorem. Let mu be a measure on a ring R and let mu star be the extension of mu to an outer measure on the hereditary sigma ring H R. Let S bar be the collection of mu star measurable sets and mu bar is the extension of mu to S bar. Then every set E coming from H R which has sigma finite outer measure, these sets have measurable cover F with the additional property that mu bar F is equal to mu star E. So, we start the proof. First, let us take a member E from H R such that mu star E is finite. Now, from the equivalent criteria of mu star which we had developed, observe that for any positive integer n, we can find a mu star measurable set f n from S bar such that E subset of f n and mu bar f n is less than mu star E plus 1 by n. If we take the intersection of all these measurable sets f n, that is intersection n equal to 1 to infinity f n, and write it as f, then obviously f is a measurable set containing E, and we have mu star E less or equal to mu bar f, but this is less or equal to mu bar f n since f is subset of f n for all n. Again this is less than mu star E plus 1 over n, and this is true for all natural numbers n. Since mu star E is independent of n, so the left hand side is independent of n. So, taking n tends to infinity, we have mu bar f is less or equal to mu star E. So, this shows that mu bar f should be equal to mu star E. Now, we want to show that this measurable set f is the required measurable cover. So, for that let us take a measurable set G from S bar such that G is subset of f minus E. then automatically E is contained in F minus G, and so mu bar F, which is already equal to mu star E, this is less or equal to mu star F minus G by the monotonicity property of mu star. This is equal to mu bar of F minus G, since F and G both are measurable, but this is equal to mu bar F minus mu bar G, as mu bar is a measure and it is subtractive. But this shows that mu bar G is such a number that when we subtract it from mu bar F, still it is greater or equal to mu bar F. This is only possible when mu bar G is equal to 0. So, this shows that F should be a measurable cover of E. Finally, let E be any arbitrary member of HR with sigma finite outer measure, where of course mu star E is equal to infinity, because we have already proved the result for a set with finite outer Lebesgue measure. Obviously, note that if F is a measurable set containing E, then mu star E and mu bar F both should be equal to infinity. So, here we do not need to show the equality. Now, from the definition of HR, we can find a countable collection of sets E n dash n belonging to capital N, such that E subset of union n equal to 1 to infinity E n dash, where each E n dash has outer measure finite. But then we can rewrite E as countable union of sets E n, union n equal to 1 to infinity E n, where the sets E n's are pairwise disjoint. We have seen that this type of operation can be done, and when we do such operations, the resulting sets E n are subsets of the original sets E n dash. So, mu star E n is finite for all n. Now, by the first part of the proof, every E n has a measurable cover F n. And so, if we take the union of all these measurable sets, that is F equal to union n equal to 1 to infinity F n, then F is a measurable set containing E. Clearly, mu bar F is infinity, and it is easy to observe that for any measurable set G from S bar, if G is subset of F minus E, then mu bar G is equal to 0. And so, this F is the required measurable cover of E. Finally, we want to show that for any two measurable covers F 1 and F 2 of a set E, we must have mu bar f1 equal to mu bar f2. Why? Because if we start with two measurable curves f1 and f2 of E, we have E subset of f1 as well as E subset of f2. This implies that E subset of f1 intersection f2, consequently f1 minus f2, which can be rewritten as f1 minus f1 intersection f2. So, this is subset of f1 minus E. Similarly, f2 minus f1 is contained in f2 minus E, and since f1 and f2 are measurable curves and f1 minus f2 or f2 minus f1 are measurable, so we must have mu bar f1 minus f2 equal to mu bar f2 minus f1 equal to 0, and this implies that mu bar f1 equal to mu bar f2. So, to summarize, what we did in this module is that we have finally shown that if a measure mu is given on a ring R, then we can extend it to a measure mu bar on a sigma ring S bar as also the sigma ring SR, which is contained in S bar. We have shown that in general, though this extension is not unique, but if we start with a sigma finite measure mu, then the extending measure mu bar is also sigma finite and it is an unique extension. We have then defined the notion of measurable curves, and we have shown that the sets from HR which have sigma finite outer measure, these sets must have a measurable curve such that the measurable curve has the same measure as the outer measure of that particular set. And in particular, we have shown that any two measurable curves of a set have same measure. And with this comment, we finish this module.